Objective of this video is to find the section capacity of the steel beam under compression. So confirm the form factor for a grade 300, 610 UB 101. So the form factor of the universal beam, that is given here, 610 UB 101 on page number 15. We can find the 610 UB 101. We have a form factor given 0.888. So for that 0.888 we need to find using the calculations how these form factors comes, and we need to verify that answers that we should get 0.888 and thereby determining the section capacity. So we need to find the section capacity NS in compression. Now for 610 UB 101 I extracted the informations on page number 14. On page number 14, so on the one steel table, 610 UB 101, depth of the beam 602 is given, 602 depth is given, width 228 is given, and the 10.6 and 14.8 and 10.6 is the thickness of the flange and thickness of the web. That is just noted here in the pictures. Now we are going to, this is the flange and this is the web. Now we are going to check whether the flange is going to buckle or this web is going to buckle. So we're going to do the two checks for this one. Let's start with the flange. Now for the flange we need to get the B over T ratio. How do we find the B over T ratio? B is generally looking for, this is the flange outstand, that we need to find it out what is the B and what is T value. So B, if you have a 228, that is 228 here, so we just need to take the half of 228, take away this half of this 10.6 divided by 2, that is 228 times, take away 10.6 over 2, so that is B value, right? And this T is 14.8, that is 14.8 that we just calculated. So that B over T ratio given 7.34. Now we no need to involve in this geometry because the one steel tables, the manufacturer already given that B over T ratio, which is 7.34. So 610 101, and that is the value 7.34. But in case you want to find out how this one calculated, so that is 7.34, and that value is B over T 7.34, and description is given for individually B over T. Now plate slenderness, there is an equation in the AS4100, lambda E equal to B on T Fy 250. Now we are working in the compression, so in the section 6 is a member subject to axial compression onto B on T Fy 250. So that's written here. We are going to substitute 7.34. We just calculated B on T, which is 7.34. Fy 300. So if you move on the page number 15, 610 UB 101, we have given 300 megapascal and 320 megapascals. We are taking the minimum value between these two, so the yield strength is 300 megapascals. Substitute that value, lambda E value is given 8.04. now yield slenderness limit that we can calculate here, we can obtain it from the table 6.2.4. Table 6.2.4 AS4100 on page number 83. For the flat plate, if the one longitudinal edge is supported outstand, so that is the typical case for the flange, and for the flange we have various residual stresses are given. Now all the one steel table is the hot roll section, so that is HR, which is written here, and for that one we have a yield slenderness limit lambda E. So that is a lambda E value, which is 16. Now effective width, we can find the effective width. So we need to check this this relationship, which is effective width is less than B, then we can say that if it is, this relation is correct, then we need to consider the form factors, and the flange will going to buckle. But effective width, which is BE, is greater than B. So if this condition is not correct, then we can say that is fully effective. So we are going to calculate BE equal to B lambda E over lambda EY over lambda E, that is coming from here on page number 82 on clause 6.2.4. We can substitute 108.4, which is B, that we calculated just before, which is 108.7, that is this B value. that I just presented here, that B value is this length, so which is 108.7. So that is 108.7. Lambda EY is 16. We get it from table 6.2.4, and we calculated lambda E value 8.04. Substituting this three value given 216.3. Now we are comparing this BE value with the B. What is the relationship here? Now BE is 216, and that is greater, which is 216.3 greater than 109 millimeters. So in that case, buckle is fully effective. That's the scenario. If it is less, then we will need to have a effective buckling. We will have a effective width. Now we will check for the web. Now this is the web. We need to find this B value divided by T, and this B value 572 is given in the one steel tables on page number 14. For 610 UB 101, we can find this 572, which is D1, the depth between the flanges, which is 572. That is given here. Thickness is 10.6 of the web, 10.6 of the web. So B over T value, which give us 54. And we can also compare this one against this one, 610 UB 101, 54 D1 on TW. That is given in the one steel table. So we can straight away take this B over T ratio for the web. Now plate element slenderness ratio, close 6.2.3 on page number 81, and that equation is taken from here. Substitute the value 54, we just calculated 54 B on T ratio for the web. Yield strength, that we are taking the yield strength here from the one steel tables. We have 300 and 320. We are taking minimum value for this one, give us 59.1. Now yield slenderness limits taken from table 6.2.4 on page number 83, where we have both edge are supported, because in the case of let's say in the case of web, we have let's draw up this I-beam here. So if I have this both edge are supported longitudinally, so that's what the both edge support is. In the previous case, only one edge was supported, this was free, so therefore we have case both edge supported flat, and we have hot roll section. So in that case, lambda EY is 45. Lambda EY equal to 45. Now effective width that we can calculate on from the page number 82, we have effective width equation B on lambda ratio. So that's taken it here. B is 572. We obtain that 572 just from that. If we taken this 572, we depth of the web times 45, that we obtain from table 6.2.4 divided by 59.1, that is this one. It gives us 436 millimeters. Now we need to compare this 436 millimeters with the B 572, and it's less. Please check here. We have this effective width is less than B. So in that case, the web is not fully effective. For example, we have this ineffective region. If we have ineffective region, this is effective, that buckling happens. So web is not fully effective. So we need to find the ineffective area of the web. So D1, which is 572, take away this ineffective width. So this is ineffective width. So let me put this. So that is 436. That is we calculated this effective width times 10.6 is the thickness of this one, give us the ineffective area 1448. So that is ineffective area. This area is 1448 millimeter square. Now effective area of the steel beams, we found the ineffective area. From here we found this ineffective area. Now we are interested in finding the effective area for the whole cross sections, including web and plate. This is ineffective area, so we need to remove this. We need to find this effective area, red one. So gross area of the steel beams 13,000. So how we going to find that gross area? If you go to the one steel table 610 UB 101, they have a given the gross area 13,000 millimeter square. So that's the gross area. Take away if ineffective area, we just calculated ineffective area in our last steps where we have 1448 millimeter square, that give us 11552 millimeter square. Now the form factors, the equation for the form factor is taken from the page number 81, clause 6.2.1, where we clause 6.2.2 form factors. We have effective area divided by gross area. So effective area we just calculated 11552 divided by gross area 13,000, give us the form factor 0.888, and that's need to be confirmed with the one steel tables. That in the one steel tables 610 UB 101, it has given the form factor 0.8880. So the answer is confirmed. Now we need to calculate nominal section capacity in the compression of that beam. So nominal section capacity is taken from clause 6.2.1 on page number 81 on AS 4110. It has an equation KF, AN and FY. AN, that is a quick note here. For our case, we are taking the gross area. So 0.888 that we calculated form factors. Gross area 13,000 millimeter square times the yield strength 300, give you the answer in Newton, divided by 1000 to get the answer in kilonewton. So that's the section capacity of the 610 UB 101. Thank you.